again. In this example, you will learn how to perform moment distribution on a frame which doesn't experience sway. This is the frame that we will be examining, and as you notice, none of the joints, A, B, C, D, or E, can translate, and that means no sway is occurring. So we are being asked to solve for the internal moments at the joints, and we will begin the process by locking all of our joints against rotation. A, D, and E are already locked, so I just now lock B and C to go along with that. Next step is going to be to solve for the stiffness factors. So I'm going to be looking at joint B first, and that will be equal to 4 EI over L, which is 14. By the way, that will be equal to 2 over 7. I'm conveniently leaving off that EI, and you'll see why here in just a little bit. But we do need to point out that the columns here have a moment of inertia of I, and the beams have moment of inertia of 1.5 I, and what is assumed throughout the entire process is that the modulus of elasticity is the same for all members. So continuing my calculation of stiffness factors for joint B, then BC, since it is a fixed member, is also 4 E, but it's 1.5 I, and that's divided by its length of 18 feet, and that actually works out to be 1/3. KCB is equal to KCE, and that's 4 EI, but we have that factor of 1.5 on the I, divided by 18, that's equal to 1/3, and KCD is equal to 4 EI over L, which is 14, and that is equal to 2/7. So joint B has 2 members coming into it, joint C has 3, and so we need to make sure as we calculate the distribution factors that we account for that. So let's handle joint B first. DFBA is the stiffness of BA divided by the total stiffness at the joint. That is equal to 0.46. DFBC, we know that distribution factors at a particular joint have to sum up to be 1, so we can simply calculate that using this equation. That handles joint B. Let's handle joint C next. Remember, we've got 3 members coming to this joint. So we'll look at member CB first. So we'll put its stiffness factor in the numerator, and then we want the total stiffness of the entire joint. So I should have 3 terms since I have 3 members. That will be equal to 0.35, and since member CE has the same stiffness factor, then we can go ahead and assign that to have the same distribution factor. So the last distribution factor I need is for member CD, and that I can calculate as the 1, which I know needs to be the sum of all the distribution factors at that joint, minus 0.35 minus 0.35 gives me a total of 0.30. And then the next thing I'm going to do is I'm going to calculate the fixed end moments. One of the things you're going to notice here is that I'm only showing the members that actually have load applied to them. Go back to this original one, member BA, member CE, those have loads applied to them. All the rest of them are going to have fixed end moments that are equal to 0, so we won't bother to sketch those out here. Now in order to compute these, I'm going to have to go to my beam charts that tell me that for distributed load it's WL squared over 12, so that moment would be 1.5 kips per foot, 18 feet squared over 12, and that is equal to 40.5 kip feet. And then for the one with the point load, it's 2.5 kips times 14 feet all over 8, and that will be equal to 4.38 kip feet. Let me go ahead and put these back on the free body diagram here. Let's remind ourselves here that the sign convention for moment distribution is that if the moment is a clockwise moment, we will consider that to be positive. So this would be positive while this would be negative. And I will consider that as I get things translated over to my distribution table. So here we've got that taken care of. I've already got the distribution factors for each joint assigned in here. And you're going to notice joint C has the 3 members coming into it. We've also got the fixed end moments that are applied to CE and AB. We will balance all joints simultaneously. Joint B is out of balance, joint C is out of balance. A, D, and E are already fixed supports, so they will take whatever moment we assign to them. So we don't need to try and balance those out. So let's look at joint C, and I'm going to sum up all the moments there at joint C. That's 0 plus 0 plus a negative 40.5 is equal to negative 40.5. That means that I need to add 40.5 back onto that joint, and these are the distributions that will happen there. Negative 0.35, negative 40.5 is equal to 14.18. You'll notice 2 of the members have that distribution factor, and then 0.3 times negative 40.5 is equal to 12.15. Let's get those sketched back in here. So the distribution would be 14.18, 12.15, and 14.18. Let's handle joint B now. And if you sum up what's happening there, it's 4.38 plus 0 is 4.38, which means I'm going to have to add on to that joint a negative 4.38. So let's figure out what the distributions are for it. Negative 0.46, 4.38 equals negative 2.02, negative 0.54 times 4.38. That will be equal to negative 2.36. And I can go ahead and get that back onto my other table here. So that would be negative 2.02, negative 2.36. That handles the distribution, but now I've got to do the carryover. And since all members are fixed, look at all this, all the members are fixed, then I know that the carryover is going to be a half for every one of those. So if we do the carryover here, that gives me negative 1.01. I can do the carryover here at negative 1.18. Then let me go to joint C and I'll do the carryover. That'll be 7.09. Here's where the table can get just a little bit confusing for us. What I know is that this is happening at C and it needs to distribute or carry over to joint D. So I'm going to just draw the arrow like this. It's going here at 6.08, and then this will carry over to joint E at 7.09. Then I would come back and do the distribution for those again. Now joint B is out of balance by that much, joint C is out of balance by this much, and I can run that distribution. What I've done for you here is I've run all those distributions. You can examine how those are being done here. Just remember the carryovers as they happen here, and then you handle the carryovers again, so on and so forth, and you just keep carrying on those distributions until the carryovers become really quite small. I think from a practical perspective we probably could have even stopped somewhere right around here, but it did continue that on, and once we have done that, we will then sum up each column to get the answer, sum up each column to get the answer. And what should happen is these should sum up to be 0. Same thing here, should sum up to be 0, and then we know that we are in balance. And that concludes this example. It's always a beautiful day to study structures.